every day.
Abisters! My favorite day! We are talking about Taylor polynomials. God, doesn't get any better than that.
Hey guys, guess what I have to go to the class? Swim. I'm going to be there.
You know, is this going to, because it's at the end of the day, is this going to be a struggle for me and I'm going to weep at the end?
Yes.
Oh yeah. So the end of the, if calc was this time every day,
oh my God,
nothing will get done.
We're just so ready to like be done.
Well, you don't think I noticed that? But guess what?
Graduation.
Okay.
Graduation. Graduation.
We might as well just go over the quiz today and start. Don't say this is his favorite day today, guys.
No, I have waited for this day all year. Alrighty, here we go. This function right here, just to get, notice I give you a lot of marginal space on this one. It's done on purpose.
See, this is why we can't get anything done. He definitely.
Want an almond?
Can you teach me to throw discus?
Graduation. 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 Show the camera. Can we show the camera?
No.
Garth is 37 years old.
We must be disrupting.
That's long.
I'm taking all.
Alrighty, I'm ready to go. Okay, so this function is f of x.
There was like 3 classes looking at our room.
And it is e to the x.
Yes.
And I chose e to the x because its derivative is e to the x, okay? It's really, really, really nice. And I'm picking this point right here as my point of tangency, and that point is 0, 1, and I chose that on purpose because the slope, when you plug in 0 into e to the x, is 1. So all the numbers are 0 and 1. They're nice. Okay, I did that on purpose. We're not going to be so nice in a little bit. So here's your tangent line. Here's your function. And as long as we're really close, like around there, it's a pretty good estimate. And what I did is I used, I think the equation of my tangent line looks something like this. The slope is 1 times x minus 1 plus 0.
It's written above there.
Yeah, it's right, or x minus 0 plus 1. Yeah, I wrote it right here. And if you plug in 2.8, you get 3.8. Well, if you would plug 2.8 into e to the x, or e to the 2.8 power, you get 16 point something. It's not a very good approximation, is it? Because since this is concave up, and this has no concavity, it just keeps going straight, as I move further and further away from 0, it becomes a worse and worse approximation. What would be better is if I could take that line and bend it so it would have the same concavity. It would give me a better approximation. That idea is called a Taylor polynomial. Okay? The idea of a Taylor polynomial is all the polynomials that you come up that are Taylor polynomials will be all tangent to the same point. The linear one, the quadratic one, the cubic one, the quartic one, and so on. They'll be what is called centered around C. In this case, C is equal to 0. It's right here, x minus c. So those curves that bring us closer approximations are written based upon their degree. So a tangent line is going to be p sub 1 because it has a degree of 1. A quadratic one will be p sub 2, a cubic p sub 3, and so on. All right? The point of tangency in this case is the x value is called c. we say the polynomials are necessarily tangent with each other because they're all centered around C. And this right here, this tangent line, is called a first degree polynomial. A second degree polynomial would be a quadratic. Notice the constant is written first. You're going to see a little different format than probably something else that you've seen in all your other algebra classes. So rather than have the degree, like the cubic be first, like x cubed, it's going to be at the end. So since the second derivative indicates concavity, correct? Right? The second derivative indicates concavity. A quadratic, a second degree polynomial is going to be quadratic, where when I take the derivative of that quadratic, it's going to be exactly the same as taking the derivative of f. So in other words, since f is equal to e to the x, and f at 0 is e to the 0 is equal to 1, if I take the derivative of that, I'll get e to the x. The derivative at 0 is going to be 1. When I take the derivative of a first degree polynomial at 0, it better be equal to 1. And if I take the second derivative at 0 of the function, I get 1. The second derivative of that quadratic at 0 better be equal to 1 also. And every derivative here in f has to equal every derivative in the Taylor polynomial. That has to be true. So if you take a look at this, how did I get this? Well, my first degree polynomial was this. And if I take the antiderivative of this, I'll get x plus 1/2 x squared plus a c, right? That would be the antiderivative. But since my point is at 0, 1, if I put 0 in for x's, 1 will be c, correct? And that's how I got this. Are we okay right now? And this is a better approximation than the linear one. Abby, you got a question.
How did you get 1?
How did I get 1? I know this is...
Constant cancels out, and then the x turns into a 1, and then the 1/2 x squared turns into x.
Yeah, I took the antiderivative of this and got 1/2 x squared. I took the antiderivative of this, got x, plus a c, right? Mm-hmm. And so that means this polynomial is equal to this.
Yeah.
My point is 1, 0. Excuse me, 0, 1.
Yeah.
So this will be 0, this will be 0, and so c's got to be 1. Okay? Yes, ma'am.
So I understand the little apostrophes mean derivatives or second derivatives. What do little sub numbers mean?
Okay.
1.
So if I have, this means I have a second degree polynomial, it's going to be quadratic. X is going to be the second power.
Then why does that one have the derivative apostrophe and a 1?
Right here?
No. Over. It says.
Right here?
Yeah.
This is the derivative. The derivative of this is equal to 1.
Okay.
That's what that means. Does that explain that?
Yes.
Okay. Are we okay with that? All right, so let's go to the next page. So what I did is this function right here is f of x equals e to the x. This very left-hand function. I'm going to blow it up way up. Over here, this right here was my tangent line, or my first degree polynomial, of 1 plus x. That's what this is. This right here is the quadratic. This is,
What does that say? Right. Oh, just kidding.
okay. And then if you take a look, it was really hard for me to get, do you see this one that's in between e of the x and the second degree polynomial? Can you kind of see that? This is p sub 3. See how close it is? It's really, really close, isn't it? All right? So what I did is I'm going to move out, and I listed the polynomials, first degree, second degree, third degree, fourth degree, fifth degree, and sixth degree, and I wrote them out. I went through and did the antiderivative and then subbed in 0 made it equal to 1, and that's what you're going to get. And then I plugged in 2.8 into each one of those. And you can see the original right here was 3.8. The quadratic, I would get 7.2. The cubic, I would get 11.379 about, okay? When I got to here, I'm pretty close to 16. This is what e to the 2.8 power is, and I just kept it the same to compare. So you can see this is a pretty good approximation, isn't it? As I curve it and bend it more and more towards that curve, it gives me a pretty decent one. Does that make sense so far? All right.
So wait, if you were to do to another degree, like x to the 7th over whatever number that would be, would it be even closer?
7 degree, yeah, it'd be even closer.
It wouldn't go over?
No. In this particular special case, now I picked a special case on purpose. I picked e to the x, something that we're going to come back to, okay, when we talk about Taylor series, because you can see I'm adding something up the whole time, right? And e to the x, the sine of x, and the cosine of x can be defined as particular Taylor series. We're a long ways from that yet, but that's where we're headed to, okay? But as I increase my polynomial, the error gets smaller, which is something we will talk about. Yep?
Why would you do this instead of what we've been doing? When is there a case that you would need to approximate a tangent instead of just creating a tangent?
Here. So when you put in the square root of 49.2 and it gives you your answer, it has a Taylor polynomial created in it, and that's what it puts in. It doesn't really put it into the square root. Okay? So one of the first things that because for a while when I went to college, I was thinking about becoming a programmer. And at that time, there weren't any small computers. There were just mainframes. And so I learned how to program in binary code. So how do you go about and determine when somebody inputs a value to take a square root or take the sine of it? One way to do it efficiently with a few amount of terms is something called a Taylor polynomial. Okay? Because right now it looks long, but there are some Taylor polynomials that are very accurate and very short. Does that kind of explain it a little bit? All right. So I'm going to look at this right here, and I want to explain what you see here. My notation kind of got funky at the end, and I apologize for that. So first of all, e to the x and c were chosen because they were really, really easy. Okay? And so what I need to do is show you how to create a Taylor polynomial, and that's what this process is. If you look in the book, they don't show you this. They just give it to you, and I refuse to do that. I want you to see where it comes from. So this right here is the definition of a Taylor polynomial. This is some constant. This is some coefficient times x minus c. This is some coefficient times x minus c squared. So if I would stop here, that would be a second degree polynomial. Does that make sense to everybody? If I would stop here, that's what a fourth degree polynomial looks like. You will always be told what C is every single time. What I'm going to show you is how we figure out A1, A2, A3, and A4, those coefficients. That's where we're headed towards. Everybody with me on that? Okay. So this right here, this notation, I think got icky because I don't know why I wrote the n like it did. This means a Taylor polynomial. This n should be down subscripted like it was up here. This simply means I took the derivative of this whole thing. So if I take the derivative of this, a sub 0 disappears because it's a constant, correct? What I have here is when I take the derivative of this, because this is to the first power, and I take 1 times a sub 1, and then that becomes 0, I'm just left with a sub 1. Would you agree? And then you understand where the 2 came from here, correct? And then you understand where the 3 came from, correct? And you understand where the 4 came from, correct? I took 4 times a sub 4, and then this decreases by 1, okay? So notice something, 4a sub 4, 3a sub 3, 2a sub 2. Really, that's a 1a sub 1, correct? That's the first derivative. Then I took the second derivative. This will disappear, correct? This is now my constant, isn't it? Because this was to the first power, 1 times 2 times a sub 2, and then that'll go to 0, will be this constant, won't it? Now this 2 gets multiplied by 3. Now this 3 gets multiplied by 4. And over here, if you notice this very last term, I took n times a sub n, and there's an n times a sub n, and this drops down by 1, correct? So when I take the next derivative, this n minus 1 is going to be multiplied by n, and it's going to drop down by 1 again, correct? And I'm going to do it one more time. And I'm going to, if I keep doing that, with every single polynomial, you'll end up with a constant. Do you agree? Because eventually you get x to the 0 power, right? And so this is the constant, this a sub n, which was the very last term, will remain, and I'll have n times n sub 1 times n minus 2 all the way to 1. Well, what is this thing right here? That is n factorial, isn't it? So my last term is n factorial times a sub n. Yes, ma'am?
I thought n factorial is n times n plus 1 times n plus 2.
Tell me what that is.
7 times 6 times 5 times 4.
I don't know why
Right?
I thought that too, though.
Okay. Are we okay with it now?
I was totally thinking that.
Are we okay? Are we okay now?
Yeah.
No, that's all right. That's all right.
Yeah.
All right. So now, if I let x be equal to c, if I let x be equal to c, this will be gone, won't it? Because I'll have c minus c and get 0, right? And this just becomes, when I plug c into here, all I'm going to get is a sub 0, correct? When I plug c into here, all I'm going to get is a sub 1, correct?
Yep.
And that's all I'm saying right here, is that when I plug c into here, can you see it now? When I plug c into here, I'm going to get a sub 0. When I plug it in the first derivative, I'm going to get a sub 1. When I plug it in the second derivative, I'm going to get 2a sub 2. When I plug it into the third derivative, I'm going to get 2 times 3 times a sub 3. when I plug it into the very last term, I'm going to get n factorial times a sub n. Because the x minus c becomes 0. And all those other things disappear, correct? All right. So, all the polynomials have the same tangent line, correct? So, p sub n of c has to equal f of c. Remember when I was at e sub 0, that was equal to 1. That was at the point 0, comma 1, and I showed you those graphs. They're all centered right here, aren't they? That's what this is saying. So they're all centered around that spot. C, comma, a sub 0. They're centered right there. 0, comma 1 was that spot. And I said every derivative, the first derivative, the second derivative, the third derivative of every Taylor polynomial has to equal the derivative of the function. Remember I said that? So this has to be true. All of them had a slope of 1, didn't they? All of them had a concavity of 1. All of them had a third derivative of 1. That has to be true here. Now, if I look at this, this means that when I take the second derivative and plug c in it and divide it by 2, that's going to be a sub 2. Or what I can call 2 factorial, because 2 factorial is 2, isn't it? This right here, the third derivative, excuse me, not the third derivative, with c plugged into it, divided by 6, is going to equal a sub 3. Well, 6 is the same as 3 factorial, isn't it? Third derivative, 3 factorial. Fourth derivative, 4th factorial. Fifth derivative, 5th factorial. So whatever the derivative is, that's what you're dividing factorial by. Are we okay with that? And that is that term a sub 1, a sub 2, a sub 3. So this is the definition of a Taylor polynomial. I gave that to you earlier. Now what I can do is, since these are the same, I can substitute those in for a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, all the way to a sub n. And you can see a pattern here. I'll make it a little bit bigger. Here's the first derivative. Here's 1 factorial. Here's the second derivative. Here's 2 factorial. Here's it squared. Here it is to the first power. Third derivative, 3 factorial, cubed. Fourth derivative, that's how we write the fourth derivative. 4 factorial, 4th power. So if I stop here, that is how I defined a third degree polynomial. If I stop here, that's a first degree polynomial. If I stop here, that's a 4th degree polynomial. Is that making sense? You will be asked to find a 4th degree polynomial, a Taylor polynomial. So I'm going to, right here, I came up with, we're going to find 4 Taylor polynomials, a 0, 1, 1, 2, 3, and 4. And it's going to be centered around c sub 1, and I'm going to show you how we're going to go through that. All right? Okay. So I kind of have a method in which I do. I write down what f of x is. F of x is equal to the ln of x.
Can you zoom out or move it over?
Does that work?
Yep.
Better? Okay. I'm going to go up to 4, so I'm going to take the first derivative. What's the first derivative of this function?
1 over x.
1 over x. Perfect. What's the second derivative of this function?
Negative 1 over x squared.
Perfect. What's the third derivative of this function?
1 over
2, right? Because you're going to multiply by a negative 2, and it's going to become positive. 2 over
x cubed.
x cubed. And what's the fourth derivative? And I'm going to put a 4 in here like that. Does anybody think they got negative 6, perfect, over x to the what? Fourth. Okay? Now, c is 1, isn't it? Correct? So what is f of 1? It's the ln of 1, right? What is that? 0. What is f prime of 1? 1. What's f double prime of 1?
Negative 1.
What's f triple prime of 1? I think you said it and I didn't hear it.
2.
2. Okay. And then what's the fourth derivative of 1? Negative 6. Okay. So, Taylor polynomial of 0 is simply 0. It's that term. Taylor polynomial of 1. I better write x here. Is going to be 0 plus 1 times x minus 1 to the first power.
I'm confused. Oh, never mind. I'm not confused. I'm confused.
You are.
I am.
Okay, so if you take a look, this right here is
How'd you
a,
get just p of x?
it's a function. P stands for polynomial. 1 means it's a first degree polynomial. So I got to raise something to the first degree. And x is my input value.
I mean, like, where does the 0 come from?
That's a sub 0 up here.
A sub 0.
Yep.
And
That's f of 0. And a sub 0, the same thing. So my second degree polynomial is going to be 0 plus 1 times x minus 1 to the first plus a negative 1 over 2 factorial times x minus 1 squared. Now I haven't simplified them yet, but I will. My third degree polynomial is 0 plus 1 times x minus 1 to the first minus, I'll write the minus this time, 1/2 x minus 1 squared plus, pardon?
Forgot to add the factorial.
I didn't because 2 factorial is 2.
That makes sense.
Okay, but this one I'm not going to forget. Okay, this one I'm going to have 2 over 3 factorial times x minus 1 cubed. And I'll simplify that in a bit too. And then this one, my fourth one, will be 0 plus x minus 1 to the first minus 1/2 times x minus 1 squared plus, I believe that's 1/3, because 3 factorial is 6. 2 over 6 is 1/3 times x minus 1 to the third minus 6 over 4 factorial times x minus 1 to the fourth. This is simply x minus 1. This is simply x minus 1, excuse me, minus 1/2 times x minus 1 squared. P sub 3 is x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed. And P sub 4 is x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 to the third minus 1/4 times x minus 1 to the fourth. Does anybody have a guess what the next term would be? Would it be plus or minus? Plus. Plus, what's my coefficient, do you think? 1/5 times x minus 1 to the fifth. Okay, I'm going to make a 4. I'm going to go to example 2 and make a 4-degree polynomial. First thing I have to do is I have to figure out what f of 2 is. Why did I choose 2? Because it's centered around 2. That's what c is. So what would that be? 1/4. The first derivative, what is it? Negative 2 over x cubed. So that means if I plug 2 in there, what am I going to get? Negative 1/4. The second derivative, what is it? 6 over x to the fourth. So if I plug a 2 into that, what would I get? It'd be 6 over 16, right? 3/8. So if what's the third derivative?
Negative 24.
Over x over what? X to the fifth. And if I plug a 2 into that, what do I get? I get negative 24 over 32. Negative 3/4. And I gotta do one more here. The fourth derivative of x would be what? Negative what? Or excuse me, a positive what? 120 over x to the 6, and if I put a 2 in there, I would get 120 over 64, which is what? I think you can divide them both by 8, I think. I think 120 is divisible by 8. I think, isn't it 15? 8 times 15, 120? Okay, so it's going to be 15 over 8. So here's my 4-degree polynomial. I start with this number. This is my constant I begin with. 1 is equal to 1/4 minus 1/4.
No, isn't that just supposed to be 1/4? I mean, 15 over 18?
This right here is 1/4, f of 2.
Why is it P of 4 then?
He's writing the whole polynomial.
I'm writing the whole polynomial. 1/4, okay, times 1 over 1 factorial.
Hello, Storm Nation.
Everybody's
Auditions for
canceled.
next year's concert choir will be held next week on Monday, Tuesday, and Wednesday. Interested students should
We'll
sign
finish
up for an audition time on
Monday.
Mr. Vick's office doors.